Hey there guys, for this video I'm going to be doing a quick recap of activities 1 through 7 in preparation for the exam. So starting out with activity 1, we have the definitions of natural numbers, rational numbers, real numbers, things like that, and list out which ones of these sets each one of these numbers is in. And then we talk about the properties of addition, multiplication, and the distributive property of multiplication over addition. These rules are very important for you to be able to use, but I don't expect you to remember the names of them. Moving on, the most important thing from activity 1 is probably the orders of operations. So parentheses first, then exponents, then multiplication and division evaluated from left to right, and then finally addition and subtraction evaluated from left to right. So multiplication does not come before division, addition does not come before subtraction, they both happen at the same time. Also, it briefly mentions that negative 25, or the square root of any negative number, is not a real number. So we have a few example problems from this for the order of operation. And again, order of operation, parentheses, exponents, multiplication and division, addition and subtraction. So order of operation for evaluating things. So the first thing you do is parentheses. I get a lot of questions about this absolute value of 7 minus 2. This is evaluated at the same time as parentheses. So parentheses first, that gives us 25 minus 7, which is 18, divided by square root of 4, all over absolute value of 7 minus 10, which is negative 3. Evaluating those, we have 18 divided by square root of 4. Well, next thing up is exponents, so we'd evaluate that square root of 4. Because square roots are fractional exponents, 18 divided by 2, all over absolute value of negative 3, which is positive 3. 18 divided by 2, multiplication and division, is 9, still over 3. Now for some more multiplication and division, we have 9 divided by 3, which is equal to 3. Moving on to the next activity. Activity 2 is about fractions. So this is talking about the definitions of fractions. It uses examples of shapes. So the numerator of the fraction is how many shaded pieces you have. The denominator of the fraction is how many pieces a whole is divided up into. It has a little bit about factoring with factor tree, a little bit about factoring using short division. I usually prefer factor trees because I feel like they're easier to see what's going on, but short division is also entirely acceptable. So prime factorization of something like 75 with factor tree, you're looking at things that multiply to equal 75. Since it ends with a 5, I'll go and divide by 5. 5 times 15 is 75. 15 is 5 times 3. So 75 is equal to 5 times 5 times 3. Then it moves on from there to simplifying fractions. For simplifying fractions, the first step is to factor all the pieces of those fractions. So here, 75 over 20, you want to factor both of those. We already factored 75, let's factor 20 real quick. 20 is 2 times 10, 10 is 2 times 5. So 20 is equal to 2 times 2 times 5. Simplifying the fraction, you write out the factorization of both the numerator and denominator. And then you cancel out pieces in the top and the bottom. You've got a 5 in common in both the top and the bottom. That leaves us with 3 times 5 over 2 times 2, which is 15 over 4. So that's simplifying fractions when you only have numbers in them. Later on we'll get to polynomials, but the process remains the same. You factor the numerator and denominator and cancel out the common pieces. On the next page, we work a little bit with the definitions of fractions, the shapes, and how many pieces are shaded. So we've got a couple different ones. First one, circle is the unit. So the top of the fraction is how many pieces you have shaded. The bottom of the fraction is how many pieces the entire unit is divided up into, which can be a little bit tricky on things like this and this. This one, for instance, the large square is the unit. Be very careful reading these. The large square being the entire square. Large square is the unit. That is divided up into 4 pieces, and 3 of them are shaded. Whereas down here, the small square is the unit, and each one of these little small squares is divided up into just a single piece. It's not cut in half or anything like that. It's just a single piece for the unit. And still 3 of those are shaded. So this fraction is 3/4, but this fraction is 3/1, or just 3. Same thing with hexagons. Single hexagon being the unit, it's divided into 2 pieces. You have 3 of those. That's 3 halves. Or if the double hexagon is the unit, then the 2 hexagons are divided up into 4 pieces, and you have 3 of those shaded for a fraction of 3/4. Has a little bit about finding the common denominator with adding fractions together, and then also some about multiplying fractions. How when you multiply fractions, you don't need to find the common denominator. You just straight across multiply them. 3 times 4 over 4 times 5. Cancel, cancel, that's 3/5. Multiply numerator to numerator, denominator to denominator. Whereas when you're adding fractions, you need that common denominator. Moving on to last page of activity 2. A little bit about division, reciprocals, and their relationship to division. Dividing fractions is the same as multiplying by the reciprocals of those fractions. So something like 6/7 divided by 2/5 is the same as 6/7 times the reciprocal 5/2, which a lot of people remember as keep the first fraction, change the division to multiplication, and flip over the second. Keep, change, flip. And then you do the straight across multiplication. 6 times 5 is 30 over 2 times 7, which is 14. Moving on from there, we have activity 3, which is rules of exponents. The most important takeaway from activity 3 is this table right here, the rules of exponents. A to the m times a to the n is equal to a to the m plus n. When you're multiplying together 2 things, you add the exponents. The next one, a to the m, quantity to the n, you multiply the exponents. When you've got those parentheses around there, to another exponent, those multiply. We're given this one, a to the m times b to the m. When you have the same bases, you can combine them together underneath the exponent. When you've got the same bases, or that's with different bases. When you have the same bases, you can subtract the exponents here. It's a to the m minus n on the top, or you can subtract the exponents on the bottom, a to the n minus m. In general, I'll use this to always subtract the smaller exponent from the larger exponent. Whichever one is smaller, whichever one is larger, always just subtract the smaller exponent from the larger exponent. And then you won't ever have negative exponents to deal with. A to the 0th is equal to 1. More specifically, anything to the 0th is equal to 1. Doesn't matter if this is an expression in here, doesn't matter what that is, it's always equal to 1. A to the negative first is equal to 1 over a. Also, a to the negative any exponent is equal to 1 over a to that positive exponent. And additionally, 1 over something to a negative exponent is equal to the thing to the positive exponent. Negative exponents move something from the top of a fraction to the bottom, or from the bottom of a fraction up to the top. If you've got different bases underneath the same exponent, just as we had up here, what we have down here, you can combine them into a over b, all to the m. The last rule, nth root of a to the m. How I remember that is roots make things smaller, dividing makes things smaller. So what you divide by is the root. Running through a few examples real quick of using those. 4x to the third times 3x to the seventh. For this one, we multiply things that are like each other. We multiply the numbers with numbers, the variables with the variables. And since they're the same variables of x here, we can multiply them together. So I group these up, 4 times 3 times x to the fifth times x to the seventh. Multiply 4 times 3 is 12. X to the fifth times x to the seventh. We add the exponents, that becomes x to the 12th. Down here, we can distribute this exponent into every single term in there. That becomes negative 2 to the fourth. Careful with the parentheses, it's the entire negative 2 that you're taking to the fourth. A to the negative third to the fourth. B to the second to the fourth. Doing this exponentiation, negative 2 to the fourth is negative 2 times negative 2, which is positive 4, times negative 2, which is negative 8, times negative 2, which is positive 16. So that becomes 16, a to the negative third to the fourth, and that should have been a positive third. A to the third to the fourth becomes an a to the 12th because you multiply the exponents. B to the second to the fourth becomes b to the 8th because you multiply the exponents. 16, a to the 12th, b to the 8th. This one, 8 times x to the 0th. The first step that you do is you evaluate the exponents. 8 times x to the 0th is equal to 8 times 1 because x to the 0th is 1. That equals 8. Whereas down here, the parentheses group the entire 8x to the 0th, so this right here is equal to 1. This problem, first thing we can do to simplify it with a negative exponent is we can just flip over the entire fraction into an x over 3 to a positive exponent. Because negative exponents are the same thing as flipping over the top to the bottom up to the top. And now we can distribute that squared to each term inside of this. So that becomes an x squared over 3 squared, which is x squared over 9. Let's do one more from this activity. 8xy over 4 to the negative first, x squared y to the negative second. First, let's get rid of negative exponents. Move this 4 to the negative first up to the top. That becomes 4 times 8 times xy. X squared stays on the bottom. Y to the negative second also comes up to the top as a y to the second. Now, combine like things. 4 times 8 is 32. X divided by x squared. Subtract the exponents. That's just 1 over x. So 32, the x is now just a single x on the bottom because you essentially cancel these out. And y times y squared gives us a y cubed. An x on the bottom. Moving on to activity 4. Now we're dealing with radicals, evaluating roots. I'll run through a few of these real quick. Square root of 25 is 5. Negative the square root of 25 is negative 5. Square root of negative 25, not a real number. Difference between this and this is there you're evaluating the square root before you make a negative. Here, you're evaluating the square root of a negative, and you cannot do that. Now we have some higher roots here. Cubed root of 64. That's looking for 3 numbers that multiply together that are the same that equals 64. So let's factor 64. That's 8 times 8 Which 8, I remember, is 2 times 2 times 2, 2 times 2 times 2. So that means that 64 is 2 to the 6th power. Or, since we're looking for perfect cubes, that's the same thing as 4 to the 3rd power. And the reason for that is 2 to the 6th is 2 squared cubed, because you multiply the exponents, which is 4 cubed. So cubed root of 64 is the same thing as cubed root of 4 cubed, and then the cubed root of 4 cubed is equal to 4. Now here we have the cubed root of negative 64, and it's tempting to say that we cannot evaluate that. However, since it's the cubed root, we can actually evaluate that, because negative 4 times negative 4 times negative 4, that is negative 4 cubed, is equal to negative 64. Because we're doing an odd number of multiplications, the negative sign is preserved here. So this is equal to negative 4. 4th root of 256. If you factor it out, you'll find that the 4th root of 256 is also equal to 4. 4th root of negative 256, however, is not a real number. And the reason for this is because we have an even root. If you have an even root, you cannot find the negative root. If you have an odd root, you can. And that goes back to odd number of negatives multiplied together is negative. An even number of negatives multiplied together is always going to be a positive. So you cannot get a negative sign by exponentiation with an even exponent. Moving on from there, this is all talking about how roots cancel. If you have the 5th root of something to the 5th power, it's equal to the number itself. If you have the 8th root of something to the 8th power, it's equal to the number itself, except for the absolute value of that. And this goes back to how you cannot find the root of a negative number if it's an even root. With the even exponent, this takes that 9, raises to the 8th power, now it's guaranteed to be positive, and then you take the 8th root of that, which is positive. Here you take the 5th exponent of negative 2, which is negative number. 5th root of a negative number is negative. 8th root of a negative number is positive. Even root of a positive number is always going to be positive. So whenever you have an even root, it gives you the absolute value of the thing. If you have an odd root, it gives you the number itself. That is laid out in this box right here. If n is a positive even integer, then the nth root of a to the n is the absolute value of a. If it's a positive odd integer, then it's just a itself. Let's look at simplifying a few of these roots. So first I'll do square root of 98. You factor this. That's square root of 2 times 49. And I'm going to stop right there because I know that 49 is a perfect square. Square root of 49 is equal to 7. Square root of 2 we cannot evaluate, so that 2 remains underneath this. We're left with 7 times the square root of 2. Square root of 3 times 27. You can combine those underneath the root. Square root of 3 times 27. That's the square root of 81. Square root of 81 is 9. Now for this, I will use the shortcut for evaluating roots, because roots are fractional exponents, and we discussed that in activity 5. Roots are fractional exponents, so if we combine these together, that's the square root of 6 times 2, which is 12. V to the 6th times v to the 5th. You add the exponents, that's v to the 11th. Y to the 5th times y to the 7th is y to the 12th. Again, adding the exponents. Square root is the second root. That's the same thing as a 1/2 exponent. So let me factor the 12 into 3 times 2 squared. When we're simplifying this root, we are looking at essentially dividing each exponent by 2. Now, not all of those evenly divide by 2. For instance, 3 technically has a first exponent. 1 divided by 2, it's not even. So that says we cannot take out any part of that 3 from underneath the root. We've only got one 3 underneath there, so we cannot simplify it. This 2 to the second power, though, square root of 2 to the second, the root and the exponent cancel out. We've got 2 divided by 2, simplifies to a 2 on the outside. V to the 11th, 2 goes into 11 5 times. That means that there are perfectly even 5 v squareds underneath there. And then we have 1 remaining. 11 divided by 2 is 5, with a remainder of 1. So we have 1 v remaining underneath there. Finally, y to the 12th, 2 goes into 12 6 times, with a remainder of 0 on the inside. So we have 2v to the 5th, y to the 6th, square root of 3v to the first power. And you can also rewrite that as 2v to the 5th, y to the 6th, square root of 3v, because the first power doesn't change anything. V to the first is equal to v. You can use the same process for this problem. 45 is 3 squared times 5. If you factor that, you'll find that to be true. So you can rewrite this as the square root of 5 times 3 squared times w to the 4th, all divided by u to the 7th. Simplifying that, we'll have a whole part on the outside, then we'll have a fractional part inside the root. Again, we're looking at dividing each exponent by 2, because the square root has a hidden 2 there. It's the second root. So 5, we've only got a single 5 down there, so we cannot simplify that. Still have the 5 inside the root. 2 divided by 2, that gives us 3 to the first power on the outside. No remainder. 4 divided by 2 gives us an even w squared on the outside. No remainder. 7 divided by 2 gives us an even u cubed on the outside, but we have a remainder of 1, so we have a u to the first on the inside. And then just rewrite that nicely. 3w squared over u cubed, square root of 5 over u. That's it fully simplified. You can use this with higher roots as well. With this, we have the 4th root. So this says we have got negative 3, 4th root, factoring 32, 2, 4, 8, 16, 32. 32 is 2 to the 5th power. P to the 15th, Q to the 8th. Divide each exponent by the root. 4 goes into 5 one time. So we have 1, 2 on the outside, with a remainder of 1. 4 goes into 15 3 times. 4 times 3 is 12. So we have p to the 3rd, the 3 even times on the outside. And then our remainder, 15 minus 12, is 3. Remainder of 3 on the inside, p to the 3rd. 4 goes into 8, and even 2 times. So we have a q to the 2nd power on the outside, and then nothing remaining on the inside. Rewrite that more nicely. Negative 3 times 2 is negative 6. P cubed, q squared, 4th root of 2p cubed. Moving on from there, activity 5 is all about rational exponents. It's showing how roots can be written as fractions. It shows you that the square root of a is the same thing as a to the 1/2, and then gives you the more general form that the nth root of a is a to the 1 over n. And then takes that one step further to redevelop that rule that we gave you in activity 3, that the nth root of a to the m is the same thing as a to the 1, or the n, m over n, because dividing makes things smaller, roots make things smaller, so it's a to the m over n. A few practice problems rewriting roots as exponents and the other way around. Some evaluation problems. Cubed root of 27. Negative the cubed root of 27, which is negative 3. Cubed root of negative 27, which, since it is an odd root, is still equal to negative 3. It's important to note the difference, though, between these two. If this was, say, square root of negative 4 versus negative square root of 4, this one would equal negative 2. This one would be not a real number. And then down here, we have the cubed root of 8 squared. So on this order of operation is very important. You can write this as the cubed root of 8 squared, which is the cubed root of 64, which is equal to 4 times 4 is 16, times 4 is 64. That's equal to 4, which is a little bit more complex. Or you can write this as the cubed root of 8 squared. Cubed root of 8 is 2. 2 squared is equal to 4. Same answer, but the second way is a lot simpler than the first way. And in this case, we can find it through both methods, but in general, you might have a larger number in here, say 25. And if you wanted to find 25 cubed and then take the square root of that, you're going to be dealing with massive numbers. Whereas finding the square root of 25, which is 5, and then cubing it to get 125 is far simpler. We can see that with this problem right away. 125 to the 2/3. Rewrite this right here as the cubed root of 125 squared. Cubed root of 125, if you factor it, you'll find that to be 5. That's 5 squared, which is 25. Whereas if we did it the other way, we'd have to find what 125 squared is through multiplication. Which is a lot more work than we want to have to put in. So that's why you always want to find the root before you evaluate the exponent. Next, we've got a little bit about reciprocals. Negative exponents flip over the fraction. Simplifying these things. So 9 to the negative 3/2, for instance. That's the square root. Well, let's get rid of the negative. That makes it a 1 over 9 to the 3/2, which is 1 over square root of 9 cubed, which is 1 over 3 cubed, which is 1 over 27. Again, another situation where you can cube it first and then take the square root, but you'd be dealing with 27 squared, or 9 cubed. 9 times 9 is 81, times another 9 is 700 and something. It's a big number. We don't want to have to deal with that. So you find the square root first, and then you cube it. Over here for the rest of the activity is a lot of rules of exponents. X to the 1/4 times x to the 5/4. If you're multiplying the fractions, you're adding the exponents. That becomes x to the 1 over 4 plus 5 over 4, 6 over 4, which is x to the 3/2. On this one, subtract the smaller exponent from the larger exponent for division. 1 over a to the 11 over 9 minus 2 over 9. 11 over 9 minus 2 over 9 gives us 9 over 9. 1 over a to the 9 over 9 is 1 over a, because 9 over 9 is equal to 1, and an exponent of 1 doesn't change anything. For something like this, you can simplify. Actually, let's move on to the last one. It's always better to simplify before you complexify. So simplify things in here. X to the 4th over x squared. Well, you can cancel that out, because an x to the 4th is an x squared times an x squared. So if you subtract 2 from 4, you get 2. 3/8 is larger than 1/4. 3/8 minus 1/4 is 1/8. So that's y to the 1/8. And on the bottom, we're left with 1, all to the negative 2/5. Get rid of the negative exponent. This becomes 1 over x squared y to the 1/8 to the positive 2/5. The negative exponent flips over the entire fraction on the inside. Now distribute that exponent to both of those. This becomes 1 over x to the 2 times 2/5 y to the 1/8 times 2/5, which is 2 over 40, which is 1 over 20. That's your answer. Moving on to activity 6, which is operations with polynomials. Now I talk a little bit about the definitions of polynomials, what it takes for something to be a polynomial. However, you have negative exponent, it's not a polynomial. Or if we've got a 1 over n squared, something like that, 1 over n squared is the same thing as n to the negative second, so that means that no, that is not a polynomial as well. All the rest of these are polynomials. When you have multiple variables in the polynomial, that's fine, so long as these are real numbers and these are natural numbers. So natural numbers meaning they have to have only positive exponents. And they have to be whole numbers as well. So yes, that one is. The leading term is the entire term with the highest degrees associated. So in this case, the leading term is 2xy to the 5th. Leading coefficient is whatever number's in the front, which is 2, and the degree is the sum of the degrees on all variables. Now x, we could say, has a degree of 1, y has a degree of 5, so the degree of these together is 6. In this one, leading term is the entire negative 2n cubed. Make sure to bring along the negative sign. Leading coefficient of negative 2, degree of 3. Goes on to talk about like terms. Like terms are what things need to be to add them together. They have to have the same variables with the same exponents. I like to think of these when we're adding as objects. Like, you have 2 of your object. You have 1 of your object. You're adding 2 of them to 1 of them. You have 3 of them. They could be apples, they could be x's, they could be x cubes. So long as they look the same, that's what matters. So when we're adding and subtracting expressions, for instance over here, we can only add things that have the same variables and the same exponents on those variables. So this 4w cubed minus w plus 2w plus 9. We can only add things if they have the same variables and the same exponents. That means that we can only add this negative w plus 2w. Negative 1 of something plus 2 of something is positive 1. So this becomes 4w cubed plus w plus 9. For the next one, we would add together the 1/3 x squared with the 3x squared. We would add together the negative 2x with the positive x, and we'd leave the negative 4 alone. For the next one, we would write this as 8x to the 4th plus 7x squared minus 3x to the 4th plus 5x squared, because this negative right here would distribute to each one of the terms on the inside. Same thing down here. This next one would be 6k squared minus 7k plus 3 minus 4k squared minus 6k plus 5. And then you combine the like terms in here. The k terms with the k terms, constants with the constants, and the squareds with the squareds. Next, we have multiplying polynomials. Most important thing with multiplying polynomials is to multiply all the pieces together. So the 3c multiplies to 6c, 3c multiplies to d, 2d multiplies to 6c, and 2d multiplies to d. Multiply all of those together. In this one you get 18c squared from the first two, plus 3cd, plus 2 times 6 dc, which is 12. And the order doesn't matter when you're doing multiplication. C times d is the same thing as d times c. So I'm going to write this in alphabetical order as well. And then 2d times d plus 2d squared. 3cd plus 12cd is 15cd. So that's 18c squared plus 15cd plus 2d squared. Combining the like terms. And then there's a little bit here about how a plus b squared is not the same thing as a squared plus b squared. You cannot distribute an exponent across addition. If there is any addition or subtraction inside of the parentheses, you cannot distribute the exponent to the terms. In that case, what you would have to do instead is write this out as a plus b times a plus b, and then FOIL it all out properly. A times a times b times a, b times b. That would give you a squared plus 2ab plus b squared. A few more examples on the back page of multiplication, and a little bit about squares of binomials. If you've got a plus b squared, then it's a squared plus 2ab plus b squared, a minus b squared, like that. And then the product of the sum and difference of two terms, a plus b times a minus b is a squared minus b squared. Activity 7 has more operations with radicals. So now we're dealing with messier, bigger terms underneath the radicals, adding and subtracting radical expressions, combining like terms with having radicals in there. So you can only add or subtract things that have the same type of roots on them. So here we've got root 5s with root 5s. You can subtract those. They're the same sort of thing. You have negative 4 of these things plus 2 of these things. That gives you negative 2 root 5. Over here we've got fifth root of 3's. Doesn't matter. We've got one of them minus 6 of them. That's negative 5 fifth root of 3. All that matters is that the things that you're dealing with are the same. Down here, we've got root 18s, and we've got root 2s. Those are not the same thing. You cannot just say that 6 root 18 plus 5 root 2 is 11 root whatever. You have to make these look the same. But fortunately, we can simplify root 18 as square root of 9 times 2. Square root of 9 we know is 3, so that's 3 root 2. Simplify this then into 6 times 3 square root of 2 plus 5 square root of 2. 6 times 3 is 18. So now we've got the same things. 18 root 2's plus 5 root 2's is 23 root 2's. Same things with the same things for the combination. Here we've got root 3's and root 5's. We cannot simplify root 5's to look the same as root 3's, so those will never be able to be combined. But we do have root 3's here and root 3's there. Those are the same type of things, so we can combine those. 8 of something minus 6 of something is 2 of something. 2 root 3's plus 1 root 5. Apples plus oranges. They're not the same things, so you cannot combine them. Up here, let's do a little bit of math to try to simplify these. So, root 20, that's square root of 4 times 5. Square root of 4 is 2. Root 12, square root of 4 times 3, that's 2 root 3. So we've got 3 times 2 root 5 plus 2 times 2 root 3 plus 6 times root 5. Simplify these down into 6 root 5 plus 4 root 3 plus 6 root 5. Combine the like things with like things. We're dealing with root 5's and root 5's. 6 plus 6 is 12 of the root 5's. Plus the lonely 4 root 3's remaining out there. They cannot be combined. Multiplication, simplification works the same way. You multiply the things together, Now we're doing something like root 3 times root 6 plus root 3 times root 5. But because they have the same exponents on these, the same roots that we're dealing with, we can combine these underneath the roots. That's root 18 plus root 15. Simplify these down. 18 is 9 times 2. Square root of 9 is 3. So this is 3 root 2 plus root 15. I'll briefly mention this guy too. Square root of h minus square root of 2. You have to rewrite that as repeated multiplication. You cannot simply distribute the exponent because there is this subtraction in here. So you cannot distribute the exponent across the subtraction. When you fully simplify it, that's what it should result in. And that is a summary of activities 1 through 7.